Section. Introduction. We're here to discuss the importance of reasoning and decision-making skills in the development of artificial general intelligence. Large language models, LLMs, have shown impressive capabilities in various fields, especially when combined with techniques like chain of thought, ReACT, and tree of thought. However, these models are not entirely reliable as they often produce inaccurate results, such as misunderstanding a key concept or missing important details. A popular strategy to address these inaccuracies is post hoc prompting, which involves generating an initial response, gathering feedback, and then refining the response. This three-step process has been hailed as a way for LLMs to self-correct their previous imperfect responses. However, recent studies have questioned the effectiveness of this strategy, suggesting that without external feedback, LLMs struggle to correct their previous responses. This implies that self-correction is unreliable when relying solely on the LLM itself and simple post hoc prompting strategies. In our initial experiments, we found that self-reflection within the LLMs had limited impact. In fact, only 15.1% of incorrect responses were corrected through reflection. We also noticed that the feedback generated by the self-evaluation process often led to overconfidence or inconsistency, which undermined the effectiveness of reflection. To address these issues, we propose a contrastive strategy. Instead of directly evaluating the responses, we examine the differences among multiple responses and use these differences to generate feedback for reflection. This approach is based on the idea that while generating accurate feedback directly may be challenging, identifying contrasts between various responses is often more feasible. These contrasts can highlight potential errors, overlooked details, or pitfalls. We call this approach self-contrast. It involves guiding the LLM to create diverse perspectives by self-curated prompts and then selecting different results with significant discrepancies for comparison. The LLM then reflects on the reasons behind these discrepancies and generates multiple re-examining instructions for reflection. Our experiments show that by creating diverse perspectives adaptively, self-contrast can reduce biases introduced by specific prompts. Moreover, contrasting the discrepancies between perspectives inspires deeper reflection, thereby increasing the likelihood of accurate self-correction. The self-contrast process consists of 3 steps: self-curated prompts, graph construction, and graph editing. In the self-curated prompts phase, we guide the LLMs to dynamically create a range of prompts based on the user request. Each prompt represents a unique perspective tailored to user requests. This means that the LLMs can autonomously design multiple suitable roles, personas, and instructions for user requests, rather than using manually written prompts by humans. In the graph construction phase, we build a contrastive graph based on the interrelations of the different perspectives. Each perspective and its result are treated as an individual node, and these nodes are grouped based on their similarity. The differences between the groups are then represented as edges in the graph. In the contrastive reflection phase, the LLM is instructed to revise each inconsistent node on the graph, eliminating the differences represented by each edge. Our experiments reveal that the main obstacle for poor reflection performance is the LLM's inability to accurately evaluate prior responses. This often results in overconfident or inconsistent feedback, which hinders the effectiveness of self-reflection. Our self-contrast approach addresses this issue by creating multiple perspectives for diverse results, reducing overconfident biases of a singular prompt. Then, by contrasting different perspectives, the LLM can generate more accurate checking instructions to resolve discrepancies and enhance reflection. In comparison with traditional reflection, self-contrast shows significant improvements in stability in both mathematical reasoning and challenging translation scenarios. Section summary. Large language models, LLMs, have shown impressive capabilities in reasoning and decision-making, but they often produce inaccurate results and struggle to self-correct. Previous post hoc prompting strategies have relied on external feedback, but our experiments show that LLMs have limited internal reflection abilities. To address this, we propose a contrastive strategy called self-contrast, where LLMs generate multiple solving perspectives and compare the discrepancies between them to enhance reflection and improve self-correction. Empirical results demonstrate the effectiveness of self-contrast in mathematical reasoning and translation tasks. Section. Evaluation of intrinsic reflection. We first thoroughly examine the ability of large language models, LLMs, to reflect intrinsically, meaning they evaluate their initial responses without any external feedback and then refine them. We also systematically study the factors that influence this reflection process. We assess the reflection capabilities of various LLMs across different benchmarks, such as mathematical reasoning and creative translation tasks. We measure the average accuracy for math reasoning and use the BLEURT score to compare the predicted sentences with the reference sentences for the translation task. Each result is evaluated multiple times using different prompts. We also report the significance level of the accuracy change before and after reflection using a one-tailed t-test. Our findings show that there are no significant accuracy changes before and after reflection. For example, the performance of GPT 3.5 on GSM-8K and SVAMP shows minor changes of -0.8% and +0.7% after reflection, respectively, both of which are statistically insignificant. This minor performance fluctuation can be seen across multiple LLMs and various benchmarks, which is not what we expected. In particular, most reasoning cases show a slight decrease, while the translation task is barely affected. Moreover, smaller LLMs, such as Llama 2-7B, show weaker reflection ability, sometimes even having negative impacts. These experiments collectively suggest that LLMs seem unable to self-correct through reflection. To understand why reflection is ineffective, we analyze the impact of the three reflection phases: initial response, evaluation, and revision. First, we use a weaker LLM to provide a subpar initial solution and observe whether reflection is influenced by it. If LLMs have stable self-correction abilities, they should be able to detect errors within the initial solution, ensuring their performance remains unaffected. However, our results show that the reflection results are severely impacted by the quality of the initial response. For example, when compared with using GPT 3.5 for all three phases, using Llama 2-70B for the initial response phase results in a significant decrease in performance. Furthermore, we also observe that the weaker the LLM used, the poorer the performance after reflection. This suggests that LLMs tend to trust the initial solution rather than detect and revise the errors when self-reflecting. On the other hand, when we use a stronger LLM as the evaluator to provide higher quality feedback, we see a notable improvement. For example, when using a stronger LLM for evaluation, the reflection of GPT 3.5 and Llama 2-70B improves by +9.9% and 11.8% respectively. This improvement is consistent in multiple settings. To understand why reflection fails, we further analyze the feedback generated during the self-evaluation process. We categorize all samples in GSM-8K into 4 categories based on their correctness before and after reflection. 1. Invalid reflection means the results before and after reflection are both incorrect. 2. Valid reflection means a wrong solution is revised to correct through reflection. 3. Toxic reflection represents that an originally correct response is changed to incorrect after reflection. 4. Others counts the number of correct responses before and after reflection. Our analysis shows that the number of toxic reflection and valid reflection cases are nearly similar. This explains why there is no discernible difference in performance before and after reflection. Moreover, when the initial response is erroneous, we observe that the number of invalid reflection cases is significantly larger than valid reflection cases, indicating that LLMs fail to correct errors in the initial responses for most cases. We also examine whether LLMs can generate feedback accurately and consistently. For each sample, we instruct the LLM to evaluate its initial response multiple times and record multiple feedbacks. We manually assess the consistency and correctness of these feedbacks and then categorize each sample into 4 cases. 1. Accurately identifies errors. LLM identifies errors and provides accurate and consistent feedback in multiple repeated evaluations. 2. Stubbornly offers erroneous feedback. The majority of evaluations provide incorrect feedback with specific errors. 3. Cannot output consistent feedback. Unable to assess consistently, as most feedback is different and quite random for the same initial response. 4. Overconfidence. No revision required. LLM is overconfident and believes no revision is necessary. Our analysis shows that for the majority of invalid reflection cases, their feedback is either overconfident or highly inconsistent, making it difficult to prompt reliable reflection. Similarly, in toxic reflection scenarios, 65.4% of the evaluation processes are highly inconsistent, leading to many correct answers being erroneously modified. Section Summary. In this section, the authors evaluate the intrinsic reflection capability of language model machines, LLMs, by investigating their ability to self-evaluate and refine their initial responses without external feedback. They find that LLMs show negligible performance changes before and after reflection, indicating that they are incapable of self-correction through reflection. The authors further analyze the impact of different components of reflection and observe that the quality of the initial response significantly affects the reflection results, suggesting that LLMs tend to trust the initial solution rather than detect and revise errors. Additionally, the authors analyze the feedback generated during the self-evaluation process and find that LLMs often provide overconfident or inconsistent feedback, leading to ineffective reflection. Section. Shi Bai De and Li Zhongfan Kui Ji Liang De Pinggu. In our research, we found that language learning models, LLMs, often struggle to identify errors in previous solutions, making it difficult for them to provide high-quality feedback. To address this, we considered whether LLMs could compare different solutions to identify discrepancies and provide indirect feedback, rather than directly assessing the correctness of a previous response. We experimented with having the LLMs generate two independent solutions, then compare the differences between them. This comparison served as feedback to guide the LLMs in self-correction. Our experiments showed that feedback generated through self-evaluation was often either highly random or overly confident, which could negatively impact the LLM's performance. To improve this, we proposed a contrastive strategy for reflection. Instead of directly evaluating a response, we instructed the LLM to contrast the differences between various solutions, identify their discrepancies, and understand the reasons behind them. We found that this new strategy led to a modest improvement over standard reflection using self-evaluation. It significantly enhanced the significance levels, suggesting it can greatly reduce the uncertainty associated with the self-evaluation process. We also found that LLMs face challenges in accurately evaluating previous solutions, often resulting in overconfident or inconsistent feedback. However, we observed that leveraging the discrepancies between two different solutions can lead to more effective reflection, notably reducing the uncertainty during the reflection. Building on this insight, we proposed a more diverse interperspective self-contrast, facilitating more reliable self-reflection. Self-contrast consists of three procedures: create diverse perspectives, contrast interperspective discrepancies, and eliminate discrepancies. In the first stage, we encouraged LLMs to autonomously create a variety of prompts tailored to the user's request, each offering a unique perspective for problem solving. These diverse perspectives prompted the LLM to generate different responses. In the second stage, LLM contrasts the differences between each pair of responses. Finally, to eliminate discrepancies, we abstract these differences into a detailed checklist for re-examining. This checklist guides the LLM to meticulously examine the causes of discrepancies, including random errors or intrinsic biases, which result in inconsistent results among perspectives. We also introduced the concept of solving perspective, which refers to deliberate prompting with a unique role, personality, thought style, etc., which prompts LLMs to solve user requests from a specific perspective. Diverse solving perspectives can endow LLMs with a broader range of thoughts for problem solving, thereby mitigating biases introduced by singular prompts. To achieve this, we adopted a self-curated prompt strategy, where the LLM itself adaptively generates multiple different prompts for each request, each signifying a tailored perspective, then samples corresponding responses based on these prompts. We also introduced an imperfect or even incorrect solving perspective, where we instructed LLMs to consider what common errors might be made for this request, then actively adopt a careless persona to generate an incorrect response with some common mistakes. This can serve as a negative demonstration for subsequent selection and reflection. Section Summary. The section discusses the challenges of evaluating feedback quality in failed cases and proposes a remedy called self-contrast. Instead of directly evaluating responses, the approach instructs the language models, LLMs, to contrast the differences between various solutions and identify discrepancies and reasons behind them. This strategy significantly improves reflection performance and reduces uncertainty associated with the self-evaluate process. Additionally, the section introduces the concept of create diverse perspectives, where LLMs autonomously generate multiple prompts from different solving perspectives to broaden their problem-solving capabilities and mitigate biases. Section. Contrast interperspective discrepancies. We're going to talk about a method we've developed called contrast interperspective discrepancies. This method uses a language learning model, LLM, to generate a variety of responses based on different prompts. However, some of these responses can be very similar, so we first filter out these similar responses. We do this by using a technique called K-medoids clustering, which groups responses based on their semantic similarity. We then select the most representative response from each group, ensuring that the responses we're left with are significantly different from each other. Once we have these distinct responses, we feed them back into the LLM. The LLM then compares each pair of responses and identifies the differences between them. It does this by answering 3 questions. Are the 2 responses different? Where do the differences lie? What factors led to these differences? This process helps the LLM to understand why the responses are different, and to identify any potential errors or overlooked details. For example, in a translation task, the LLM might compare 3 different translations of a phrase and identify that the main difference between them is the use of different verbs. Once we've identified these differences, we use them to create a checklist. This checklist helps the LLM to resolve any inconsistencies in the responses. It includes instructions for checking things like alignment with the user's intent, contradictions in the LLM's responses, and any miscalculations. This checklist is more precise and informative than simply asking the LLM to check its previous response. Finally, we use this checklist to prompt the LLM to reflect on its responses and revise any inconsistencies. This results in a set of consistent responses. However, the LLM needs to be careful when making revisions, as even minor changes can lead to new inconsistencies. We tested this method using 2 challenging tasks: mathematical reasoning and creative translation. We used several benchmarks to evaluate our method, including the precision of the final answer for mathematical reasoning tasks, and the BLEURT score for translation tasks. We conducted our experiments using several different models and prompts, and compared our method to several baselines. In addition to our method, we also considered 3 versions of a method called self-consistency. The first version, SC vote, involves sampling a number of decoding results and then voting on the best one. The second version, SC select, also samples a number of responses, but then selects the most appropriate one. The third version, SC reflect, involves sampling a number of responses, reflecting on them, and then generating a new response as the final answer. Section summary. The section discusses a method called self-contrast, which aims to eliminate discrepancies in responses generated by a language model. It first filters out similar responses using clustering, then selects responses with significant differences for comparison. The language model is instructed to contrast the differences and identify the factors contributing to the inconsistencies. Insightful checklists are abstracted from these contrasts to resolve the discrepancies and prompt reflection for consensus. The method is evaluated on mathematical reasoning and translation tasks using various benchmarks and metrics. Section: Main Results. In the section titled Main Results, we discuss the performance and efficiency of our method, self-contrast, in comparison to other approaches. We measure performance in terms of accuracy and the average number of API or LLM calls, which we use as an indicator of computational cost. Our findings show that self-contrast consistently outperforms the basic reflection method. For instance, in mathematical reasoning tasks, we see an average improvement of 7.2% with self-contrast, while the basic reflection method shows no clear improvement, even decreasing by 0.51%. We observe a similar trend in creative translation tasks, where self-contrast improves performance by 0.95%, while basic reflection decreases it by 1.6%. When compared to multi-agent and ensemble baselines, self-contrast also shows significant and consistent improvement. It performs well across different LLMs and tasks, from commercial models like GPT-4 to open-source models like Llama 2, and from reasoning to generative tasks. However, there is one exception: Llama 2 to 7b. We believe this is due to the model's weaker ability to follow instructions, which makes it difficult to accurately contrast 2 inconsistent solutions. Despite this, self-contrast is highly versatile and can be applied to various task types. In contrast, the self-consistency method struggles with non-numerical tasks, such as translation, due to its voting mechanism. Its variant strategies, SC select and SC reflect, also fall behind our method. One of the advantages of self-contrast is that it requires less manual effort and has a more reasonable call overhead compared to the multi-agent debate. It can be seen as a multi-agent contrastive mechanism that encourages a more explicit and purposeful debate by highlighting the differences between agents and summarizing their disagreements. We also examine the impact of different components of our method. We find that self-contrast inspires more accurate and stable reflection than direct evaluation. It includes a self-curated prompt process, which encourages diverse problem-solving perspectives to reduce self-evaluation biases. It also includes a checklist generation process to facilitate re-examination. When we replace the self-curated prompt process with direct sampling of multiple responses from LLMs, we find that performance improves as the number of sampled responses increases. However, it still falls short of the performance achieved by self-contrast with the self-curated prompts process. We also find that removing the checklist generation process has a significant impact on mathematical reasoning tasks, but only a slight impact on translation tasks. This is because translation tasks tend to focus more on local features, so the LLM can effectively reflect based on comparisons of lexical and syntactic features, even without a checklist. Finally, we find that self-contrast reduces the occurrence of invalid and toxic reflections. In particular, it decreases toxic cases by 78.9% and invalid cases by 30.8% when using GPT 3.5. This suggests that by exploring, comparing, and summarizing, self-contrast greatly reduces uncertainty in the reflection process, thereby enhancing the error correction capability of the LLM. Section Summary. In our study, we found that self-contrast outperforms vanilla reflection in terms of accuracy and computational cost. It consistently improves mathematical reasoning and creative translation tasks, achieving an average improvement of plus 7.2% and plus 0.95% respectively. Additionally, self-contrast demonstrates better generality across different language models and tasks, with notable improvements on widely used commercial models like GPT 3.5. It also requires fewer manual efforts and reduces call overhead compared to multi-agent baselines. Furthermore, self-contrast reduces the occurrence of invalid and toxic reflections, enhancing the error correction capability of the language models. Section. Contrasting two incorrect solutions is also instructive. Learning from comparing different incorrect solutions. Our method, which we call self-contrast, encourages learning by highlighting differences. The basic idea is that mistakes in different answers are not the same or are random, allowing them to be compared and used to remove doubts or biases. To test this, we took 200 questions from a dataset called GSM-8K. Each question was manually marked with a right answer, 2 wrong answers with similar mistakes, for example, mistake 1, and a wrong answer with a different mistake, mistake 2. We set up 4 experiments. 1. Review 1 wrong answer and then reflect on it. 2. Compare a right and a wrong answer using self-contrast. 3. Compare 2 wrong answers with similar mistakes using self-contrast. 4. Compare 2 wrong answers with different mistakes using self-contrast. Our results, shown in the 2 incorrect solution comparison, reveal that comparing a right and a wrong answer, or comparing 2 wrong answers with different mistakes, both significantly improve performance by 13.5% and 5.4% respectively. On the other hand, comparing 2 answers with similar mistakes doesn't really change anything. This shows that the benefit of self-contrast comes from highlighting the differences between dissimilar answers. So, even if both answers are wrong, as long as the mistakes are different, self-contrast can help to remove them. In other words, self-contrast can reduce the random mistakes that come from the inherent uncertainty of the language model we're using, maximizing the contrast effect with different problem-solving perspectives. Our previous analysis showed that only comparing dissimilar answers can encourage reflection. In our approach, we use a process we've developed ourselves to create multiple ways of looking at the problem, which we'll call perspectives for short, giving us a range of answers to compare. We looked at the distribution of these perspectives in the results we generated ourselves. For most requests, the language model generates 4 perspectives. We also looked at how often certain keywords appeared in the names of these perspectives. For mathematical reasoning, we found that the language model does indeed create many unique perspectives, leading to a range of different answers. These different answers can make our comparison strategy even more effective.